Epicon tutorial.
When solving a variable coefficient differential equation today by Laplace transform, and for Laplace transform, we will first of all taking the Laplace transform of the differential equation. So let's start by taking the Laplace transform of the differential equation as Laplace transform of t y prime prime plus Laplace transform of y prime minus 2 Laplace transform of ty prime minus 2 Laplace transform of y. So if you are familiar with Laplace transform method, when we are obtaining the Laplace transform of a polynomial and a derivative, so we are going to obtain the Laplace transform of the derivative, and then because there is a polynomial here, we differentiate based on the power of the polynomial. So if the polynomial is of order 1, we differentiate once. If it is of order 2, that is t squared, we differentiate twice. But because this one is of order 1, so we're going to differentiate once and multiply by a negative sign. For further information on this, you can just pick a Laplace transform textbook and then read that. So this will be transformed as a negative d ds of the Laplace transform of y prime prime is s squared y bar. So we said y bar is L of y. So s y of 0 minus y prime of 0. Then the Laplace transform of y prime, which is a first order, is straightforward, s y bar minus y of 0. And then the Laplace transform of ty prime. So we're going to do it the same way we treated this one, d ds of the Laplace transform of y prime, which is a s y bar minus y of 0, and then minus 2y bar equal to 0. So that's the Laplace transform of the differential equation. So we now want to apply the initial conditions. The initial conditions are y of 0 equal to 1, y prime of 0 equal to 2. So applying that here now, so we have a minus d ds into s squared y bar minus y of 0 is 1. So this one becomes a s, y prime of 0 is 2. So we have 2 plus s y bar minus 1. That's y of 0 is 1 plus 2 here now, d ds s y bar minus 1 minus 2 y bar equal to 0. So we differentiate the terms we have inside the bracket. This is a product. So in that case, we're going to be having s squared, the y bar, the s. Then we now keep y bar constant and differentiate s squared. So we differentiate s squared. So let's still have our bracket here. So if we differentiate s squared, we are going to have 2sy bar. Then if we differentiate s with respect to s, we'll have 1, and 2 being a constant will become 0, plus sy bar minus 1 plus 2 into the same way here. We are going to keep s constant and differentiate with respect to differentiate y bar. So that will be s, the y bar, the s, plus we now differentiate s and keep y bar constant. So if we differentiate s and keep y bar constant, so differentiate s will be 1 times y bar, that's y bar. Then 1 is a constant, so when we differentiate it, it turns to 0, minus 2 y bar equal to 0. So let's open the brackets now. So have a negative s squared, the y bar, the s, minus 2 s y bar plus 1 plus s y bar minus 1 plus 2s, the y bar, the s, plus 2y bar minus 2y bar equal to 0. So of course, we know that this one will cancel out. This one will cancel out. So we are now left with the following. And then this and this can be subtracted so that we'll be left with s y bar. So we have a s squared, the y bar, the s plus, so let's bring this now, 2s, the y bar, the s. So we're left with just s y bar here minus s y bar equal to 0. So we can collect common term here. To have s squared minus 2s into y bar ds minus s bar equal to 0. I can just simply write this one as sy bar plus s squared minus 2s the y bar ds equal to 0. So we can separate, let's start separating the variables. So separating the variables, we'll be having s over s squared minus 2s ds plus 1 over y bar dy bar, so equal to 0. And that can be written, this can be written as 1 over s minus 2 ds plus 1 over y bar dy bar equal to 0. And so from here we can integrate. Since we have separated the variables, integrating will give us ln s minus 2 plus ln y bar equal to 0 plus ln c. And then this can be written as ln y bar s minus 2 equal to ln c. And then taking the exponential, we're going to have y bar s minus 2 equal to c, and y bar equal to c over s minus 2. Because our y bar we use to represent Laplace transform of y, so we have ly equal to c over s minus 2. And then taking the inverse Laplace, we're going to have y of t equal to c l 1 over s minus 2. And then the inverse Laplace of this is exponential 2t. And then using our initial condition y of 0 equal to 1, that is when t is 0, y is 1. So we're going to have 1 equal to c exponential 0. This implies that 1 is equal to c because exponential 0 is 1. So that means c is equal to 1. Substituting that in our, this is the general solution. So substituting that into a general solution, so we have y of t equal to 1 times exponential 2t. So this is exponential 2t. So this is the particular solution of the differential equation by using Laplace transform method. Thank you for listening.